Hello, ladies and gentlemen. Hopefully, you enjoyed that video that you watched last Thursday. The one that had to do with limits of lights, just kind of a laid back day. We're going to be kind of diving into our light and optics unit now. Um, and for this light and optics unit, one of the big things that I like to do at the end of the unit or towards the end of the unit is having you actually do a research and a presentation on one of the light and optic phenomenon. However, just given the circumstance of distance learning, the presentation platform might look a little bit different, but we'll kind of cross that bridge when we get there. So hopefully within probably not this week, but probably by next week, I will be introducing those presentations and then giving you some time to work on those as well. I'll give you a few days to work on those when the time comes. All right, but starting off, you can watch this quick video here. Just a little short introduction to talking about light that is all around us in our everyday lives. What light is, when we talk about light, light itself is both a particle and a wave. This is called the wave-particle duality theory. And we're not going to dive into this a lot right now. When we get into our modern physics for our next unit and we start talking about things like the photoelectric effect and things like that, we'll dive more into it as to why it is acts like both a particle and a wave. But for now, all I want you to know is that I just need you to know that yes, it is both a particle and a wave. So we treat it as a wave that has both magnetic properties and electric properties. So, like these transverse waves that go along here, we have magnetic, and we also have electric waves or electromagnetic waves that are perpendicular to each other. But then there's also things out there that, like the photoelectric effect, that show that it is a particle. Like I said, we'll dive into that more when we start getting into modern physics. Okay. So like I said, it's electric and magnetic fields that are perpendicular to each other. Light doesn't have to require a medium. We know this because it can travel through the vacuum of space. Light travels from the sun in order to get to our planet Earth. So we are going to treat it as the speed of light as 3 times 10 to the 8th meters per second, or it would be, I guess that would be 3 million meters per second in a vacuum. So when we're talking about light, we always represent it with the variable c, and yes, that is from not Isaac Newton, from Einstein's equation of E equals mc squared. We won't get into that equation quite yet. That equation, once again, will be when we get into talking about modern physics. But we use the letter C to represent the speed of light, 3 times 10 to the 8th meters per second. A lot of times what we use to represent light in this specific unit is we'll use what's called the ray model. And the ray model is just simply using arrows or rays like you would in math class. So in the ray model, we just assume that light travels in a straight line. We are going to say that it can bounce off of something, or we know that as a reflection, so it can bounce off of a barrier. And then it can change directions. And in light, we call that refracting. Right? So if it changes mediums that it's traveling in, so if a ray of light is going from air to water, it's changing mediums, it's going to change directions. Okay, so that's kind of the model we use for when we're talking about light in this given situation. And then it can also be separated. So like in this given picture, this would be a good example of separation. If we have white light going into this prism here, and it comes out as all different colors of the rainbow, then that light has been separated. Okay? But we call it the ray model because when we represent light a lot in this unit, we will just use a ray. So just an arrow, just like you would in math class. And then we'll have a little bit different terminology for different things like incident and reflected rays and things like that. Okay. Just some more terminology things when we're talking about light within the ray model here. We have there's a few different kinds of materials that you can think of or that we'll deal with: transparent, translucent, and opaque. And depending on what kind of material the object is, will determine what the light does and how the light interacts with that material. So if you have something that's transparent, that's going to be like, glass, windows on your house. If you're talking about like if you have like a clear glassware in your house that you'd like drink water out of or something like that. That's transparent. It lets all light through. Translucent is a little less common. Um, Translucent is something that lets light through, but not all of it. Usually it lets light through, but doesn't form a perfect picture. So some of the light passes through, but some of it is reflected or absorbed. So a great example of this would be like if any of you have like um, if you've seen like shower glass doors that they're not completely see-through, but they're kind of like that foggy glass, that would be considered translucent. It lets light through, but no image is formed on that, or no image can be seen through it. And then the last one would be opaque. Most objects that we deal with in our everyday life are opaque. So basically, if it does not let light pass through and it either absorbs or reflects most of the light, then it is opaque. Okay. The reason we see objects is because they are opaque and they reflect some light and they absorb some other light as well. Okay, so a couple different types of reflection, since it is the most common, since opaque objects are the most common that we deal with in our everyday lives. Reflection is happening all around us. Right? Reflection is the reason that you see different colors. Okay, so when white light comes into contact with some object, that object is going to reflect some colors of the rainbow and it's going to absorb some colors of the rainbow. So, for instance, right now I am wearing a blue shirt. White light hits my blue shirt, or hits my shirt, and it is going to absorb all colors of the rainbow except for the color blue. It is going to reflect the color blue. And that is why you see the color blue, because it is reflecting the color blue. Same with you were talking about the color red. If you have a red pen, right? The reason your pen is red is because all the light is reflecting, or all the white light is reflecting red light back and absorbing all the other colors of the rainbow. There's two different types of reflection that we will talk about: regular and diffuse reflection. Regular reflection would just be like looking at a mirror, right? A mirror that you have mounted on in your bathroom. Okay, it perfectly reflects things. Could also be a window if you're outside and it's a nice sunny day and you can kind of see yourself in the reflection of a window, and it produces an image that would also be considered regular reflection because it's producing a perfect image that you can actually see. And when we talk about reflection, we have two different terms for the rays that we use. We have incident rays, which are the incoming rays. So I think of it as both start with the letter I. Incident means incoming. And then reflected rays are going to be just the rays that bounce off. Okay, so incident and reflected rays. And then we have diffuse reflection, which is similar to regular reflection. The only difference is that diffuse reflection happens because we don't have a perfectly flat surface. So when we're talking about mirrors and we're talking about windows, a lot of times those surfaces on the molecular level are so perfectly smooth that every single ray can bounce off at this perfect, nice angle. They all bounce off at the same angle, so it forms a perfect picture. Well, when you're talking about, a different object, a different everyday object, maybe it's like the shirt you're wearing, right? On the molecular level, your shirt has a very rough surface. Okay, so when those different incident rays come in to your shirt, they're going to reflect at all different kinds of crazy directions. They're not all going to reflect at that same perfect angle. So, because of that, it's not going to form a picture to your eye. You're going to see color from it, but it's not going to form a perfect picture on your eye. Okay. So just talking about reflection and kind of how that works, I already said, talked a little bit about how a couple of the terms, we talked about the term incident and reflected. Sometimes they use the letters P and Q. So P would be my incident ray. They like to use the letters P and Q when we're talking about optics and things like that. Not 100% sure why. And then Q would be my reflected. All right, so I'll just call those incident ray, reflected ray. Okay, because there are different terminologies. And when we have an incident ray come into contact with some sort of surface that is going to be reflected off of, sorry, that was my dog. It is going to reflect off at the exact same angle that the incident ray came in at. Now, here's the important part to understand is that we have something along our surface called a normal line. Okay. A normal line, which you can see right here, is just simply the line that is perpendicular or 90 degrees to the surface that it is reflecting off of. Okay. So we're basically dealing with two 90-degree corners right here. And if we're saying that the incident ray or the incident angle is, we'll just call it 30 degrees, well, that means that my reflected angle is also going to be 30 degrees. And those angles we're talking about is the angle between the ray itself and the normal line. Okay. It is not the angle between the ray and the barrier itself. That is not what it is. We are not using that angle. You have to use this angle between the ray and the normal. Same for the reflected. It's the angle between the ray and the normal. Okay? Oh, probably want to get rid of all that. Okay? So just kind of give you an idea of how a mirror works when we are actually looking into a mirror and how this law of, how reflection itself works is when you are looking at a mirror, right? Let's say you're looking at your foot. Your foot is reflecting off a whole bunch of different rays in different directions. Okay, it's an opaque object, right? But some of those rays are going to head straight for that mirror. And when they hit that mirror, remember we just talked about we have that normal line down the middle, and then it is going to have some sort of incident angle, and then it's going to reflect at that exact same angle. And when it reflects at that angle, some of those rays are going to come into contact with your eyes. Okay? Well, what happens is your eyes are perceiving that ray as if it were coming through the wall and into your eyes. So that is why when we look into a mirror, it appears as if there is somebody who is us exactly the exact same distance away. So if we're 1 meter away from the mirror, it appears as though our image is also 1 meter away from the mirror. Okay, and we call this a virtual image. We're going to get into, eventually we'll start talking about virtual images versus real images. But basically, a virtual image cannot be portrayed or can't be cast onto a piece of paper. This is just a virtual image that you are seeing. It's not actually there. We couldn't actually take that image and project it onto a piece of paper, or we can't project it onto a wall or anything like that. All right, it's kind of hard to understand right now, but hopefully once we get into talking more about mirrors and lenses, it'll make a little bit more sense. Okay, so that's just flat mirrors. What we are going to focus on more is we are going to be focusing more on curved mirrors and curved lenses and things like that throughout this unit. That's what a good chunk of this whole light and optics unit is. So we'll be dealing with, instead of having just a flat mirror, we'll do with curved mirrors. I'm sure you guys have heard these terms before, concave and convex. Kind of the way that I remember them is concave. The mirror itself, it looks like it's caved in. It looks like somebody just came in here and punched it, and so it got caved in. And then you have convex lenses, and those are the ones that bow out. Okay, so we will talk more about these concave and convex mirrors tomorrow, or the day after. I'm not 100% sure yet. But what we will do is we will eventually get into actually drawing what are called ray diagrams. And so you will actually be able to look at where an image is, or sorry, where an object is, and where the image will be formed when you were looking in that mirror. Okay, so hopefully this made sense. Today's exit ticket shouldn't be too tricky, just kind of getting some information at you guys so that we can kind of start diving more into this light and optics unit. Hope you all have a great day, and let me know if you have any questions.